So today's lecture is on how we perceive colors. So let's see a few ideas about this. So we have presented already the red, green, and blue channels, and we have said that an image is just an intensity in each one of the channels. So the closer it is to zero, that means the less amount of intensity we need from that channel. And then by combining different intensities, we can go from completely black, that is 0, 0, 0, to completely white, that is 111 or 255 to 255 to 55. And then you have mixtures also. For instance, let's say that you have color that is, let's do it with red and green. So in general, a color will be a vector formed by L, R, G, and B. But something that is somehow yellow has the, so let's start with a simpler one. So something that is red, will be a vector that is red and then 0, 0. And then depending on how big R is, then you will have more red or less red. So it can be completely red, and then you would have 255, 0, 0, or it can be kind of faint red, could be, I don't know, 10, 0, 0, could be a little bit red. And the same for green. So for green, a green color, it would be something like this. And then you could have something yellow. So something yellow has the same amount of intensity in the red and green channels. And depending what is white, you will have a very intense yellow or a less intense yellow. So same for magenta, same for cyan. And then you can have all values different, and then you would have any kind of color. Okay, very good. These red and green and blue channels, when they are displayed, they exploit explicitly this channel structure. So it is very common that in some display devices, like the cathode ray tubes or LCD, so you have three arrays of LEDs, for instance, that these LEDs, they are pure red LEDs, so they can only emit in the red spectrum, or completely green or completely blue. So, but these three arrays, they are intermixed. So in the device, physically, you have one red point and then one green point, so you see it here. And then the channel information is transformed into how much intensity you want from each one of the locations. And because they are so close, when you look from the distance, you are not able to see the small dots anymore. And what you see is a mixture. That is the mixture that gives you the appearance of having any color. But in reality, the device only can emit in red, green, and blue. So what you have to do is you take the three channels from the image, you transform it into the red channel that is an intensity. So an intensity is just a black and white image. It doesn't have any color. And then it is displayed by an array of red LEDs. And the same for the green, the same for the blue. And they are made by small dots. But because you cannot see the dots, the right technical ways that word is that you do a low pass filter of the ideal image, and then what you see is the low pass filter. So you kind of smooth the details so that you don't see the dots anymore. And then how you arrange your arrays, you can be very creative here. So different devices distribute the arrays in different ways. Yeah, you can imagine also that depending on how you structure your device, you can consume more or less energy. So depending on here, for instance, if you compare this distribution compared to this one, there is much more black area in this XO1 LCD than in the standard LCD. So that means that this one, in principle, because the illuminated area is smaller, the energy consumption will also be smaller. So what about when we print? So when we print, we do a kind of similar thing. So we print also, but now instead of red, green, and blue, we print in black, magenta, yellow, and cyan. And we will see later in the course why. But the thing is, you can transform a color now for printing. So for displaying in an active device like an LCD, you use red, green, and blue. But when you want to print, you construct another color, and this is magenta, cyan, and the other one I don't remember. Cyan, yellow. And this could be your vector, but also that we will see later again during the course. This is the non-redundant representation of your color, but you could have a redundant representation of the color with magenta, cyan. So you can think of colors as vectors in some three-dimensional space. Yeah.
Why do we need black?
The reason is that it is cheaper than so when you print. Okay, so let me do that. So a color, red, green, and blue is a point here. So this is your color point. This is your vector, and then magenta, cyan, and black. Magenta, cyan, and yellow is a rotation of the coordinate axis. I don't know how to draw it, but okay, some rotation of the coordinate axis. And then black is adding another axis. So it is like when you this is a vector, okay? So when you say RGB, my color is whatever in RGB, what you're saying is my vector is R times the unit vector in R plus G times the unit vector in G plus B times the unit vector in B. So that will give you the instructions to reach that point. But if you add another vector, say black, and this one, you may put most of your weight here to get closer, and then you add just a little bit of ink.
For example, if you have like 0, for magenta, cyan, and yellow,
Yeah.
it will be the same as black, right?
Here, yes. Here, no, because I could have 0, 0, 0, and then 125. And then this 125 would tell me you have to put half the intensity in black. So actually, if you want to print in black and white, you use this thing, and you are not spending any color ink. Yeah. Very good. Okay, then, yeah, so these patterns, cyan, yellow, magenta, so they are also printed on the same, following this idea of having arrays that they are intermixed. So it is the same idea as we had with the LCD, but now implemented with ink. So now because you have four channels, so you have 4 arrays. And when you superpose all of them, so you have this kind of patterns here that are called rosettes. Actually, now if you pay attention to the big advertisements at the metro, and you get very close to the sign, you see this kind of patterns, and now they are not exactly that one. So it seems that the technology has changed. but still you see small points, and you recognize this idea of printing in some arrays. So yeah, so how to print an original this image. So you separate into your 4 channels, and then each one of them is representing somehow in its own scale how much intensity you need for that channel. And then you have the printing array, you print it in those colors, and then you superpose, and you have here the superposition. And if you look from very far, you don't see the rosette pattern, because if you do a low pass filter, you lose the details. Okay, then how do we see? So we have the eye, and the eye has at the back of the eye there is a region called the retina. That is where the cells that can see that are sensitive to light reside. And you see that those cells are not in the first layer of the retina, but that there is some transduction from where the light is coming from here, and these cells are a little bit behind. So these ones are transparent, and the light can reach these ones. Okay, so these ones, we have different kinds of cells. We already recognize here, we have the kind of these cones that have been represented with colors, and the rods that are represented as blue sticks, if you want. And also all these, so these cells get excited with light, and then they transform the light into some electric signal that is connected to some neurons, and then all the neurons are collected here in the optic nerve, and information is sent to the brain. And that means that where the optic nerve is, we cannot have receptors. So the receptors are in this blue thing, or in the red one. So there we don't have receptors. That means that there is a point here in which we don't see anything. Okay, so here we cannot see light. And there is another region that is called the fovea. So the fovea is the region where most of the cones are. So we will see that again. So this is again another representation of the same of the retina. So you have the cones, you have the rods, and this retina, this part here is the fovea. So you see that the density of points here, the cells here are much more tight, and they become less dense as you go away from that point. So that point is the fovea. So that means that you have more receptors, you have more details, and also this is the distribution of types of cones that we have. So you see that mostly we have green cells, so cells, cones that are sensitive to green light. And then the second ones, more important, are the red ones. So we have more red receptors, and then the blue receptors are the fewest. Here is another representation of this concentration of this density of receptors. So you have here the fovea. So in the fovea, the concentration of cones is maximum, and the concentration of rods is minimum. So we have very few rods at the fovea. We have mostly cones. And it is not that we have 0 cones everywhere else, but we have many less. And the rods are distributed away from the fovea. And here we have this blind spot that is where the optic disc is. Any question? Okay, another representation of that. So here we have very tight cones, and as you go away, you have rods that are the purple ones, and then from time to time you have some cones. And as you get closer to the fovea, the density of cones becomes bigger and bigger until they become so packed as they are there. Very good. So that means that the fovea is where we see the details. So the fovea, we see the details of some region, and as you go away, you lose those details. So you don't have those details anymore. And then what you do is you move your fovea. So the face of this guy here is in focus, and then you move the fovea to somewhere else. Sorry. You move the fovea to somewhere else, and now this girl is in focus, and you keep moving your fovea everywhere. And it is the brain that collects all that information and puts it together. But if you look at some instant, what the signal that is getting to the brain is this one, and the brain is integrating over time. And actually, this movement of the fovea, the eye is all the time moving. It is called the saccadic movement. So the fovea is moving all the time, so that we can see collectively. This is just a way to simulate mathematically the same effect of the fovea. So you see, this is the ideal image, and this is how we would see it with less details here. And here you have the equations to do that, but this is not important for us. Now, if you are interested, you can pursue this line, but otherwise it is not showing. Okay, there is some other effect, that is these receptors are very close to each other, and they are connected to neurons, and then they excite those neurons. And what happens is that if one neuron gets excited, the nearby neuron gets inhibited. So somehow you can represent that as here. So if one neuron is excited at some particular location, the nearby neurons get inhibited. And this is in real space, so that is kind of the point spread function that you asked the other day. So this is kind of point spread function of our neurons, and you can represent it this way. So here the high values are black, so it is just a representation thing. And what kind of signal can, also what kind of function has this behavior? And the Laplacian of the Gaussian has that behavior. Okay, so this function, the one we have from there, is the Laplacian of the Gaussian, of the 2D Gaussian. And if this is the response in real space, so what is the response in frequency space? So it is this one. So this one means, so it is just the Fourier transform of this one. So that means that what we see is a kind of bandpass filter. So it is a bandpass filter. The very low frequencies we don't see, the very high we don't see either. And then we have a maximum at middle ranges. And this is just the equation of the Fourier transform of the Laplacian of the Gaussian. Then you apply your bandpass filter to your image. So actually what we see are the borders. So we don't see, so the brain, but the information that gets to the brain are just the borders. And it is composed with the fovea. Okay, so it is the fovea thing plus the borders. Any question here? No? Okay, good. So then let's do the following experiment. So it's going. Let's do the following experiment. So we have an image. I will do an image of 4 times 4 pixels. So let's say that we have here our image, and we have RGB values for each one of the pixels. But then, so we have 4 images, 3 images, 4 times 4. One for red, this would be the red channel, another one for the blue, green channel, the green, and then another one for the blue. Okay, so the green and blue, or one of the channels so 2 of the channels we keep as they are. But then, for instance, for the red one, we compute the average of all those values, the average, the average, the average, and then we put the average in all those 4 pixels. Okay, so now you have, let's say that you had at the beginning an image of size n rows, n columns, so you have 3 n squared numbers. Now here you would have n half times n half, and then here you have n squared, n squared. So now in total you have 2n squared plus n squared divided by 4. Okay, so you have less information because you have fewer numbers, so you have less information. Very good. So we will do that. So this is our original image with the all the channels, and now you construct pixels or averages that are of size 2 times 2. Okay, so the boxes are of the same size I draw, and then 4 times 4, 8 times 8, 16 times 16. So you can imagine in all channels. Okay, so you can see how the quality of the image degrades as you are averaging more and more. Okay, and it makes sense. So dividing the information by 4 doesn't seem to be too terrible. By 16, you're still you already start to see a lot of artifacts. And by 64, you see a lot of artifacts, and 256. Okay, well that makes sense because they have bigger pixels. Okay. Now let's do the same for all the channels. So for each one of the channels independently. So let's do the 16 time pixelization, that is this one, 16 times pixelization in the red channel. So the other two they stay the same, but the red channel has been pixelized by a factor of 16. And okay, you see artifacts, but it is not so bad. Now for the blue, and again, you see artifacts, but not so bad. For the green, it is terrible, you see? So this is kind of proof that we have more green receptors than red and blue receptors. Because when you shrink the information in the green channel, the image is much more affected than in the other ones.
It needs also, we have higher frequencies in the green, like the leaves are smaller, where in the blue one, it's like pretty much the same.
Partly true, yeah. Also has to do with that. Yeah, very good. And then the reason why we have more green receptors, because we grew up as a species, we grew up in the forest, and in the forest, all the trees are green, and you need more precision in the green color than in all the other colors. And also that explains why we see so badly by night. By night, the one that is responsible, so the rods are responsible for the night vision, so they only see intensities mostly, and this see intensities kind in the blue area, so the blue light. And so by night, you don't get any excitation here because there is no light, red, green, or blue light, there is blue light, but there is no red and green, so you don't get any excitation here. That is where you have your most sensitive area. And then all the rest, that is where you don't have so much sensitivity, it is the one that is receiving the night light. Okay, so here we are. Yeah. So how this information is sent to the brain. So we collect the information from the eye, and then it is sent to the back of the brain. I don't know if there is any good hypothesis why the visual information is in the back of the brain and not in close to the eye. There must be something, but and then this visual region, it is divided into multiple modules. So these multiple modules, they first process the information in some way. The output of this is somehow sent to the next layer. Everything is very much interconnected, but you can think of this in that way. So the output of this is sent to the next layer, and the output of this to the next layer. And at some point, there is some interpretation of the signals that are there. I think, no. Yeah, we can comment this, and then I will come back to this. Maybe. So our eye sees in 3 channels because we have 3 kind of receptors, the red, green, and blue receptors, and we will talk later about the responses of those. But the brain doesn't see in red, green, and blue. It makes a transformation. Internally, we don't know what the transformation it is, but what we know is that somehow it separates the intensity from the color. So somehow all this information is combined into a kind of luminance signal, and the color goes separate to the luminance. So the brain sees differently from the eye. And then we can play with the pixelization in the different channels. So for instance, here let's pixelate. So what we will do is do this play, do this game, but now this will be intensity or luminance, and this will be somehow encoding the color. So we will only pixelate the luminance channel. So if we reduce by factor 2, it looks almost the same. By factor 4, we see a lot of problems. A factor 8, also a lot of problems. 16, a lot of problems. So what we collect from here is that probably, and it makes sense, the luminance, how we see the luminance in the brain, somehow it is more influenced by the green receptors because we have more green receptors. So we saw the same kind of effect with the green. So probably the luminance is more affected by the green receptor. Do you remember the formula that we had to convert from a color image to a luminance image? So it had some weight, and the weight of the green channel was higher. So this is connected to this. And what if we do the pixelization in the color channels? So if we do the pixelization in the color channels, even a very bad pixelization, we don't see. So we are very sensitive to luminance, and this luminance is more affected by green. And this is a collection of all the images we have shown so far. So the colors, they are called chrominance. Okay, so the two channels of colors, they are called chrominance. And then very bad images we get for the luminance and we get for the green. But for the blue and red, they are bad, but not as bad. And for the chrominance, they're almost good, I would say. Very good. I wanted to comment before we get into this, I wanted to show you something else. So let me see if I can find it easily. Say, and face recognition. Yeah, something like this. So it is not there. So if you click, okay, this one. So somehow this is an artificial neural network, but it has the same kind of effects as we have in the brain. So this artificial neural network, we will not see how they're constructed, but somehow they receive an image and they do some processing, and then this processing propagates through different layers. So you can imagine that this is a kind of representation of what is happening in the brain. So you have a neuron, this neuron is excited by some other neurons, and then it activates in following some pattern, and this pattern is transmitted to other neurons and so on. So it is a kind of similar processing. So you have an image, and then this network has been trained to recognize faces. And then what has been observed is that the first layers, they tend to see these kind of patterns. So they activate when you see these patterns. So these patterns are not very much informative, and actually they resemble a bit like the ones we have for the activation. Do you remember the Laplacian of the Gaussian? So the Laplacian of the Gaussian means if a neuron gets excited, the nearby gets inhibited. This is this response. This area is excited, and this one is inhibited. So the low level activations, they have to do with these excitations and inhibitions. And then the next layer will see the activation of these neurons, but the next layer is receiving from multiple areas. So it is multiple of these ones. And then these ones get activated when they see kind of combinations of these kind of patterns. So, and you start to recognize a mouse, an eye that is shifted, a nose. So the second layer somehow is processing this one, combining into more meaningful patterns. And then this one is collecting information from all these ones. So they start to see faces. And this is an artificial neural network, but it has been shown that our brain also sees in that way. So somehow this processing that I was mentioning before, the V1 neurons, they are more sensitive to this kind of edges that I showed in the neural network. And then as you go away from V1, you're activated by higher and higher patterns that have some meaning in the real world. Okay, then why do we say that we have three kinds of, you see the time, why do we say we have three kinds of cells? Because when you excite those cells with light of different wavelength, what you see is this kind of response. So if you excite at each one of these wavelengths of light, so this light is, so long wavelength is red, short wavelength is purple, and then you take a single cell and you sweep along the different colors, and you see how it fires. And these are average responses. Not every cell is responding in the same way, but kind of average responses. You would have some cells that respond this way. So these are the red cones. So the red cones, they're very much sensitive to red. And they're also sensitive to this kind of blue thing, purple thing. Then you have the green cones. The green cones, they are not completely insensitive to red, but they are mostly responsive for green light. And then you have the blue cones that are mostly responsive for this kind of colors. Okay, so then let's say that the brain sees that there is a red cell, a red cone that is firing at a given rate. Okay, so you know that the neurons are, so the intensity of the firing of the neuron is measured by the frequency. It is not actually, so the current is the same. It is the frequency with which they respond. So the brain sees, okay, there is a red cone that is firing at this rate. It is not too much, it can be higher, but it is okay, this level. So how does the brain knows which is the color you're looking at? Because there are four colors for which the firing rate is the same. So you don't know which one of these four colors, just looking at that cell, you don't know which one of those colors it is. So the trick comes from looking at the other, at nearby cones. So let's say that you have this red cell, this red cone, but you have a blue cone nearby, and you have a green cone nearby. So you have three cones, red, green, and blue, close to each other. So the red cone is firing at this rate, but then you look at the other two. If, let's say that the color is this one. So if the color is this one, then the blue one is firing so it is very much activated, and the green one is almost silent. So now you recognize this pattern and say, okay, there is a blue firing a lot, red very middle, and then green almost silent. So that is this color. It is not this color, for instance, because if it is this color, then the blue would be silent. So the blue here would be silent. And the red is the same one for all of them. And the green that here was silent, here now it is firing a lot. So how we see the colors is by looking at nearby cones and seeing how each one of those are firing collectively. Any question? No? Okay, so then yeah, so this is some way of trying to organize the colors in some nice way that we will see now, how this way has been.
So basically, you look at the colors of the numbers.
You?
Basically, look at the colors.
Yeah, so you look at the heights. So the height here tells you what is the firing rate of each one of the cells.
And then is the red of the light.
This is the wavelength of light.
No, like, I mean, the other.
This one?
Yes.
Yeah, so light of this wavelength has this color,
Okay.
and light of this wavelength has this color.
Okay.
Okay. Okay, so how did we, so in this organization that we will see now, how we got to that organization. Do you remember that we had this magenta, cyan, and, blue, and yellow? So they are not chosen at random. So we were displayed in monitors with red, green, and blue, and our cones are red, green, and blue. But then we were printing in cyan, green, and yellow. Why those? Well, cyan seems to be the opposite of red, and we will see the opposite in which sense. Green, magenta is the opposite of green, and yellow is the opposite of blue. Okay, so opposite in which way? Okay, so let's say that we have all the colors. So we put all the colors, and we start exciting with all these colors. Okay, so we excite with all those colors, and we measure what is the firing rate of the different cells. So this is red. Okay, so if this is red, then the red cones will be firing a lot, and then as we get into the blue, they become silent. Green, they're silent, and for these colors again, they are firing a lot. And we look for the excitation for these colors of the other two channels, of the other two cones. So the green one is mostly responsive here, and the blue one is mostly responsive there. So that is another representation of this response. Okay. Okay. Now we have to look for a color such that the excitation pattern is the opposite of this one. Okay, so what is this? This is very high, low, and low. So we have to look for a color that has the opposite pattern. So this is high, low, low. So it has to be low, high, high. Okay, and the color that turns out to do that is this cyan. So cyan is the opposite of red. And it is the opposite because the firing pattern is the opposite one. And the same here. So here, let's see, it is low, high, low, and then it will be high, low, high. Then it is magenta. Magenta is the opposite of green. So these colors, this organization of colors, has been chosen in such a way that when you move 180 degrees, you have an excitation pattern that is the opposite from the one on the opposite side.
So what's the difference between the RGB scale and the inverse of the RGB? I'm sorry, what's the difference between the magenta, cyan, and yellow scale and the inverse of the RGB scale?
Yeah, so the difference is, so in both scales, you will be able to reach colors. This is what I try to represent here. So if your color is a vector in this color space, then you can get to the color through the red, green, and blue. I forgot to write blue. So either you get red, green, and blue, or you get magenta, cyan, and yellow. So you will always get the same color, but the amount of intensity that you need to put in each one of the channels is different. It is kind of the opposite. Okay, so the red, green, blue, somehow it is low, high, and low because you want to represent green. In the magenta scale, you have to put the opposite values to get to the same color.
That's what I was saying. Like, for example, if in an 8-bit scale, if we have, well, I don't know what's the half value of the bits, maybe 123, maybe. If I had 123, 123, and 123 on the RGB scale, would it be the same of having 123 on the magenta?
No, it will be a different value. Okay. I don't know which values they are. There is a matrix that transforms 123 3 times to the other one. That is this matrix that we will reason later when there is another part lecture in the course where we will transform colors between different representations, and you will see how these matrices look like. Okay, and then there is so now that we understand how the visual system works, now you can try to fool it. And then this kind of images, me myself, I don't see this kind of effects. So you look at this point, and then because you are saturating somehow your receptors with these negative colors, when you look at that point, when you go to the original image, you see kind of color changes. So this is a black and white image, and it seems that some people see it with some colors. I don't know. Yeah. This effect is an after image effect. But so it is playing with the saturation of the cones. So they are firing at a given rate, and then immediately after changing, it seems that some people see colors. But you can also play with the visual system in many other ways. So, for instance, here, would you say that this side of the cube is darker than this one? Would you agree with that? So this is kind of white, this is kind of dark. No? Okay. Now I will hide this region, and then when you hide that region, there is no trick here, okay? So that it is not that I have changed the colors, but when you hide that region, you see that this color and this color are the same, exactly the same one. So why is that? That we see it like white. And the reason is in the brain. So in the brain, so I said, we only see the bandpass filter of the image. So we see the borders. So what you see are the colors in the borders. And then the brain has to interpolate the colors in between. So the interpolation, it sees that the shadow. So there is a shadow here, so that means that the light is coming from there. So if I see that this color and this color are the same, but I know that the light is coming from there, it must be because this side is darker than this one. So that is what the brain is reasoning. Okay, but you only see the borders, and you only see the colors at the borders, and then all the rest is interpolation. So why normally we don't see this kind of effects in the real world? Because in the real world, this image is very artificial. It is very flat everywhere, so we have very few clues. But in the real world, there are borders everywhere, so we can get a lot of information from all those borders. But this is a very artificial image, and we don't do very well in there. And yeah, also this I like a lot. Would you say that there are some blue and green spirals? It seems that there are some blue spirals here, right? And some green ones. Okay, so let's see. So those are these two. Okay, both are green. Both are green. But they are not blue and green. It is green. So it is simply I have hidden the remaining that is not the pattern that I wanted to show. Okay, so the remaining of so what is black here, it has a lot of colors. But when you put all those colors together, because we see only the borders and we are saturating some cells, so some cones are firing a lot, and then the nearby are inhibited. So we are very much fooled by what is the real problem there. And again, this happens because in real life, we don't have this kind of patterns. So this kind of patterns are artificial, and then we can, knowing how the visual system works, we can try to fool it. And also something that is very interesting is that how much brighter would you say this spot is with respect to this? It is twice brighter, 3 times brighter? How?
No.
Same? No, they're not same.
Twice.
Twice or 3 times? Yeah. So reality is that we see in a logarithmic scale. I don't know what is the ratio between these two. I think it is, I don't know if it is 1.5 or something like that. So, but in general, we don't see, or we don't perceive in a linear scale, but in a logarithmic scale. So this is intensity of light, and even this applies also to sound and all that. So light and sound. So our response, this is the response of our senses. It tends to be something like this. So at some point, so in some region it behaves pretty linearly. So all this is linear almost. So if you double the intensity, your response is double. But at some point it saturates. So at some point it cannot respond faster than it is responding. And do you know that the sound is measured in decibels? Yeah. So the decibel is a logarithmic measure. So a sound that is at some point, a sound that is twice as intense, you hear it almost the same. So at some point you are saturated. You cannot respond more quickly. Your cells cannot respond more quickly. And again, it is very funny that these curve moves adapts to the amount of signal that you have. So let's say that you are inside a tunnel. If you are inside a tunnel, there is very little light, so the intensity is very low. So your eyes get used to the darkness, and then you see in the darkness inside the tunnel. But let's say that now you get out of the tunnel. Get out of the tunnel for very few seconds, you are almost blind. Why you are almost blind? Because your signal that was here, now the signal is here, and here you don't have response. It is saturated, so you don't see details in this area. And then what happens is that the curve adapts. So the curve moves from where it is and adapts now to the new conditions, so that you can again see details there. And the same happens when you get into the tunnel. So you are here. When you get into the tunnel, you are in an area where the response is flat. So you don't see details again, and you have to get used to the darkness again. So we see in logarithmic scale, and this curve, this logarithmic response is adaptive. And also it depends on frequency. So the frequency in images, we have not seen that concept yet, but it is the first time that you see it. So the frequency in images has to do with how fast the variations are. So these variations are very slow, while these variations are very quick. So that is frequency. And then what is the difference between, so what we are doing here is we are creating, so the difference between maximum and minimum. So we have a sign. So if you go along this line, what you have is a sign. Okay, so what we are seeing, this is the spatial coordinate, say x, and then what we are seeing is kind of sign. So what we are doing as we travel in that direction is making the sign weaker. Okay, so the difference between maximum and minimum are smaller. Do you remember that we said the contrast is the difference between maximum and minimum? So in this direction, we are decreasing the contrast. Okay, and then everyone has a different response. Okay, but for me, it is something like this. So at some point, you don't see the contrast anymore. So you don't see differences here. So at the low frequency, we start losing the contrast much earlier. And then at this range, we see the contrast much farther. But at some point, you are not able to see the contrast anymore. And for high frequency, it is the same. It starts decaying. So there is some regions, some frequencies for which we see more contrast. And this has to do with the lateral inhibition of the cell. So this one excites the nearby inhibits. So it has to do with that. And here you have all kind of visual effects that are very fine. Now you understand what kind of things they are trying to play with on our visual system. That's all. Any question?